Hello, and welcome to the EMC Live webinar, Electromagnetic Interference Testing Basics, Part 1, Capturing Pulsed Intermittent Signals with Frequency Swept, Frequency Stepped, and Time Domain Scan Methodologies. My name is Dawn Hoffman. I'm the Marketing Manager at Interference Technology, the creator of EMC Live. EMC Live is an online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Bill Wongard. Bill is the EMI receiver and radio monitoring product manager at Rohde & Schwarz. He has more than 20 years of RF and receiver experience at Motorola and Rohde & Schwarz and has authored numerous patents at Motorola. This webinar is presented by our platinum sponsor, Rohde & Schwarz. Rohde & Schwarz is one of the world's largest manufacturers of electronic test and measurement, communications, and broadcasting equipment. EMC and EMI test equipment and systems from Rohde & Schwarz determine the causes and effects of electromagnetic interference. For more information, visit www.emc.rohde-schwarz.com. This webinar is one of many. To check out our others, please visit www.emclive2015.com. A recording of this webinar and downloadable PDF will be available on our website. This webinar will be interactive. You will be able to ask questions, and we encourage you to participate. Take a look at your GoToWebinar navigation pane. If at any time you have a question, we ask you to type in the box and hit send. To make the screen minimize and maximize, click the arrow button. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. Now Bill will begin the presentation.
Okay, thank you for the introduction. Again, this is Bill Wongard, and today's presentation will be on capturing pulsed and intermittent signals and comparing the abilities of the different methodologies to do that, namely frequency swept, a spectrum analyzer, frequency stepped, an EMI receiver, and time domain scan. Okay, so for the agenda for today's presentation, we'll start with the anatomy of a pulse and why that's important for pulsed and intermittent signals and talk about the real-world signals in the spectrum of those pulses. Then we'll get into the architectures and methodologies of frequency swept mode or a spectrum analyzer, frequency stepped, again an EMI receiver, and time domain scan. And then we'll talk about the importance of setting the measurement and dwell times correctly depending on the pulse repetition rate of the pulse signal that you're trying to properly characterize. And then to drive it all home in the end, we're going to have comparison videos. So we'll have a constant input of a certain type of signal, and we'll see what it's like to capture these signals on a frequency swept, frequency stepped, and time domain scan methodology. Okay, anatomy of a pulse. So real-world signals can create real-world problems. And examples of these pulsed or intermittent signals are switched mode power supplies, radar systems, serial data emissions, valve opening or closing, short duration events such as that, systematic arcing like a brush motor at a constant RPM, and any short duration events with heating considerations. So again, there's lots of real-world signals, short or intermittent or periodic and pulsed, that appear in the real world and have to be properly characterized. Okay, the anatomy of pulse, the pulse spectrum. So here you have the frequency domain representation of a pulse. It's a sync function, and you can see that the frequency separation is a function of the PRI, or the pulse repetition interval. That's the period of the pulse, and the pulse width sets the null in the spectrum. So that's the duration of the pulse. Now, what does that look like in real world depending on the center frequency? On the left, you have a diagram of a time domain picture of a pulse train, and that again is a sync function, or a pulse in the Fourier transform of a singular pulse is the sync function. Then you have a constant carrier or frequency, and that shows up as a single frequency in the frequency domain. So if you put them together, if you have a center frequency at FC and then you put a time domain gate on there or a pulse, what you have is a sync function centered about the center carrier of the frequency. And why that's important is you will get certain frequencies that are pulsed, and that's what will show up in the frequency domain. So when you're characterizing this and you see this sync function is an indication of a pulse in the time domain. Okay, now setting the minimum dwell time for each frequency, you have to set the dwell time, which is the time that you dwell at that frequency or measure that frequency. That the measurement time has to be longer than the pulse repetition rate, which is the time in between pulses, assuming that you have a periodic pulse train. So if the pulse occurs every 10 milliseconds, then we're going to have to dwell for at least 10 milliseconds at each frequency. Okay, so that's what the anatomy of pulse and how to recognize a pulse in the time domain by looking in the frequency domain, in the frequency spectrum. Now we'll move on to the different architectures and the methodology of the swept, stepped, and time domain scan, and again talk about the measurement or dwell time. So here's the two different architectures of a swept analyzer, or a traditional spectrum analyzer that sweeps through the frequency, and a signal analyzer, otherwise known as FFT analyzer, vector signal analyzer, time domain analyzer, real-time analyzer. They technically all have slightly different true meanings, but in practice they're used interchangeably. But you can see from the architectural standpoint, in the frequency swept, the local oscillator is different, and then in a traditional swept spectrum analyzer, you have this analog envelope detector and filter, and then in the digital side of things, you have an ADC with the digital filtering and then memory and processing. So there's some back-end differences that we'll talk a little bit more about. So again, a modern EMI receiver architecture, you have a traditional lineup, and we have other presentations that go more in depth to that. But again, the analog to digital conversion and all the DSP, the digital resolution bandwidth filtering, the digital detectors, that's what sets the difference in a traditional, or I should say a modern EMI receiver architecture. The four main differences in the lineup of the spectrum analyzer, again frequency swept versus an EMI receiver frequency stepped, is the local oscillator, the detectors, the IF filtering, and the preamp and pre-selection. And again, I don't have time to go into all this in depth, but we'll cover the main difference that pertains to the difference in these methodologies with the ability to capture intermittent signals. And that falls in the section of the local oscillator and deals with sweeping versus scanning. So the local oscillator controls the measurement frequency, or the frequency at which the analyzer is measuring. And you have to be careful to spend enough time at each frequency to detect that pulsed emission. So in a frequency swept methodology, you are continually sweeping the LO throughout the frequency range. And then you have to calculate what is the measurement time at each frequency. Well, the measurement time at each frequency is going to be the sweep time that you set of the analyzer divided by the number of sweep points. And then what is the spacing or step size between measurement points? Again, you have to calculate that frequency step is going to be the frequency span divided by the number of frequency sweep points minus 1. So as an example, if you are sweeping from 200 megahertz to 1 gigahertz and you have 801 points, that's going to work out to be about 1 megahertz per point. And again, the sweep rate is going to be constant across that span. So what happens is you're going to have a reduced frequency resolution. So again, in a frequency swept spectrum analyzer, you continually sweep through the spectrum. You have to calculate to make sure that you are spending enough time at each measurement point and that you have enough measurement points to suffice the frequency resolution of the standard that you are trying to comply with. Now this is different than frequency stepped or an EMI receiver in that the LO is not continually tuned throughout the or swept throughout the spectrum. Rather, it's tuned to a certain frequency, and it stops and it dwells, or it settles and it dwells, and while it's dwelling, that sets the measurement time. So you directly set the measurement time, and you are guaranteed that you are spending that amount of time at that frequency. You also directly set the frequency step size, so you no longer have to back calculate the span divided by the number of points minus 1. You are guaranteed that when you set this up that you will have a measurement time or a dwell time at each frequency, and you're setting the frequency steps. So it takes away some of the complexities and possibilities to create errors by not having your number of points and sweep time set correctly. So as an example, you can have 4 million points over a sweep range. You have many more points in an EMI receiver versus a spectrum analyzer mode. And the resolution bandwidth can overlap to reduce frequency-related amplitude errors or the picket fence effect. And again, you are dwelling per frequency. And then another change in the architecture is the automatic gain control, which is very useful, particularly in situations where you'd be overloaded. But again, that part of the architecture is going to be outside the presentation material here. Okay, so going forward, that was frequency swept, frequency stepped, time domain. How is that different from frequency stepped? Well, the discrete Fourier transform is a numerical mathematical method that calculates the spectrum of a periodic signal. You use the DFT to simultaneously measure many frequencies in parallel. So that's the big difference between frequency stepped and time domain. In that time domain, you are measuring or calculating many frequencies simultaneously in parallel, whereas in frequency stepped, you are doing one at a time. Now, the fast Fourier transform, or FFT, is an efficient algorithm to compute the DFT using symmetry and repetition properties. So the FFT is much faster than the DFT due to the reduced number of multiplications, and that's why you never hear about using a DFT. It's always the FFT in this type of application. In time domain scan, where does the term time domain come from? So here you have a analog to digital conversion, and you are taking a time domain series of samples, and you have a time window. So you compute all these time series samples into an FFT, and then you compute the output spectrum. So you gather the data in the time domain at a fixed frequency with the wide IF bandwidth, and then you calculate the spectrum for that IF bandwidth, or really that FFT analysis bandwidth. So you are simultaneously getting all these frequency measurement points at one time or one calculation, and that's the increase in speed that comes from the time domain methodology. And what's been marketed heavily up till now is that significant increase in speed, but what we're going to see today is not only is it faster depending on the frequency range and resolution bandwidth in a frequency swept methodology, but it's also far superior in the ability to detect and capture intermittent signals. So I mentioned that this was the IF bandwidth. What happens if your frequency range that you are sweeping over is wider than the IF bandwidth? What happens is you have this IF bandwidth, and then you tune the LO to a step of the next IF bandwidth. And IF bandwidth isn't technically correct, but it's good enough for what we're trying to get across. So you go to one frequency, you calculate the spectrum, now you go to another frequency and you calculate the spectrum, and you'll stitch that together. And this point, or this slide, will drive that point home. So here you have the entire spectrum that you are trying to characterize, and you're going to break that spectrum up into sections. So now you have one section here, and you take a time series samples of the time domain. Again, that's where it gets the name time domain scan. So now you're at one frequency with an IF bandwidth. You take samples in the time domain, you put it into a fast Fourier transform, and you get the frequency out. Well, now you go to the next frequency block and you take a time series of samples, put it to the fast Fourier transform, and you put it to the frequency domain, and you stitch them back together. So you essentially scan through the spectrum, but the scan steps are much larger than in a frequency stepped, where you are measuring one frequency at a time. In a time domain scan, you are stepping through based on the FFT bandwidth, which is less than the IF bandwidth, but you're stepping through in much larger frequency chunks of spectrum. Okay, so that's the difference between frequency swept, frequency stepped, and time domain. Now we'll talk about the importance of that measurement or dwell time. So in a frequency step scan, here we have an input signal that's pulse modulated with a 12 millisecond pulse period, and what we have is a measurement time of 10 milliseconds. So every 10 milliseconds, we're going to measure a frequency, move to the next frequency, move to the next frequency. But the pulse period is every 12 milliseconds. So what that means is there's going to be lots of 10 millisecond sections where you don't see that pulse, and therefore you should be missing data. But when you sweep from 30 megahertz to 1 gigahertz, as is shown here, you don't see any missed frequencies. You don't see any discontinuities. However, they are there. And the reason you don't see them is pixelization. When you drop down the display to a certain number of pixels, that pixel represents a wider frequency range. So it represents more frequency points that are actually measured, and because you're doing a max hold, you're always going to capture the maximum. Therefore, even in this this graph, you have the wrong measurement time, you still see a closed continuous trace. So now what happens if you zoom in? Instead of going from 30 megahertz to 1 gigahertz, we're going to go from 44 to 67. Now all of a sudden you start to see these dropouts, and this is what is there. So let's see what that looks like in the time domain. So here's a picture of a time domain plot with the exact same input conditions. Here, however, we have a closed trace. We're going to start with the closed trace of a 12 millisecond measurement time. So now our measurement time is as wide as the pulse period. So we are not missing anything, and now we have a reliable closed trace. So now let's decrease the measurement time to 10 milliseconds. So every 10 milliseconds we are dwelling on a frequency about an IF bandwidth and calculating that bandwidth. Well, there's going to be times in those 10 milliseconds where that period, that pulse, never happens. And here's what happens. In this 10 milliseconds there was no pulse, so it calculated the spectrum to be 0, and it calculated it to be 0 to here. Now that may sound bad, but it's actually good, because here you're trying to detect that there's a pulse that you didn't know about. On the prior one, when there was 10 milliseconds, you didn't really know because of the display and the pixelization. However, in time domain, because you are measuring all these frequencies in parallel, all these frequencies about the measurement frequency, or the center frequency of the LO, is going to be calculated as 0. And what this does is this tells you, hey, I've missed something. I have a discontinuous trace, a discontinuous type of sync function. Therefore, I clearly don't have the correct measurement time. So this is actually an advantage of time domain, because when you see these large discontinuities, you know you're missing something. So very rarely do you know the pulse period ahead of what you're trying to characterize, and sometimes you do, sometimes you don't. But let's go and say, hi, how do you verify? Now that I know I don't have the measurement time correct because I've seen this large discontinuity in the spectrum result of the time domain trace, how do I go back and make sure I've got the measurement time? Well, you can slowly increase the measurement time until that discontinuity goes away. That's fine. Or you can go into Spectrum Analyzer zero span mode at that frequency, and now you can see the pulse periods over time. You can take markers, calculate the delta, 12 milliseconds. Now you know that you have to set the measurement time to 12 milliseconds. So at the end of this, what's important is that you have that measurement or dwell time set correctly to capture what you are trying to properly characterize. Okay, so now we've covered the anatomy of the pulse, what that looks like in the frequency domain, how to recognize pulses looking in the frequency domain. We've talked about the swept architecture of a spectrum analyzer, the stepped methodology of an EMI receiver, time domain scan, and the importance of setting that measurement or dwell time. Now, to really bring it home, the difference in the ability to capture these signals in time and reliability, what we're going to do is we're going to show some comparison videos of the same input signals going into frequencies swept, stepped, and time domain. So we have a series of 6 videos. So the first 5 videos all have the exact same input signal, and what that is, it's a 10 microsecond pulse duration with a pulse period of 10 milliseconds. So every 10 milliseconds there's a 10 microsecond pulse, and we're going to center that at 700 megahertz. And the resolution bandwidth that we're going to choose across the different methodologies is 100 kilohertz, so we can accurately compare the results of these different methodologies. So in the first video, we're going to sweep from 30 megahertz to 1 gigahertz with the frequency swept. What we're going to do is set the sweep time to be auto, whatever the analyzer thinks it can do based on the K factor of the bandwidth that it's using or the filter that it's using. And in this particular instance, it shows 1.3 milliseconds. Now, to make sure you capture everything, a common methodology is just to sweep many times over and use max hold. So that's what the first one is going to be. The second one is going to be using mil standard 461 as a reference. So the sweep time in a swept mode per table 2 mil standard 461 is going to yield a result of 146 seconds. So you have a 146 second sweep time, and we'll see the difference in those two settings and what that does. Then we're going to see the difference, the time improvement, by going to a time domain methodology and setting that dwell time to be 15 milliseconds per the standard. So again, what we're doing is we're sweeping from 30 megahertz to 1 gigahertz, comparing frequencies swept with time domain for the equivalent input signal of a 10 millisecond pulse period, 10 microsecond pulse duration. And what this is also going to show is the effect of that pixelization, which is what I mentioned earlier. And then by doing that, we're going to zoom into, in the next two videos, from 650 megahertz to 750 megahertz. And now you don't get that pixelization, so you're going to miss stuff easier because 1 pixel doesn't represent a wider frequency range on max hold that's capturing everything about it. So what you're going to see is that when you zoom in, you're actually missing things. And then to finalize the video series here, what we're going to do is we're going to change that pulse period to 1 second per the mil standard 461G pre-release out for industry review. And we're going to see the effects of these different methodologies on being able to capture that type of signal that's been specified in that standard. So let's go ahead and start with the first one. So you can see it's going to be 1 minute and 34 seconds long. Again, the conditions: 10 milliseconds PRI, 10 microseconds pulse division, pulse duration, 30 megahertz to 1 gigahertz, resolution bandwidth per the standard 100 kilohertz, default sweep time of the analyzer 1.3 milliseconds, and we're going to do a max hold and many sweeps until we are confident that we've observed it. And what we're going to see is it's going to take more than an entire minute to capture. So the point here is that you almost have to know it's there, and it can be misleading. So here's the start of the video. It's already sweeping, we have it on max hold, and we know something's there because we are controlling the input. Every 10 milliseconds there is a 10 microsecond pulse happening, and you don't see anything, and you're not going to see anything for a while. So if you are working with your spectrum analyzer and you're trying to verify that there's no intermittent signals, no pulses, you know, you look at this and you probably won't spend much time, and I think that's what happens. A lot of these intermittent signals get missed. So we're just going to sit here and wait till something shows up that we know ahead of time is already there. And if this seems long and tedious, this is part of the message when you go to compare to the subsequent videos here. So again, every 10 milliseconds there is a pulse happening and we don't see it, we don't catch it. And there it is, finally. So again, this methodology, auto sweep time, max hold, sit and wait. Finally found it. Okay, so now let's go to the next video, which is going to take longer. So this one, we're going to, instead of auto sweep and doing max hold, we're going to set the sweep time manually to 146 seconds per the mil standard 461 spec, which is 0.15 seconds per megahertz times 970 megahertz, 146. What you'll see is that given this pulse period, 10 milliseconds, you're going to capture it. It's a high probability of capturing it. But that's, again, assuming that the pulse period is within the time of the spec. So here what we see, frequency swept, here's the sweep time, 146 seconds. So you're going to have to wait the entire 146 seconds before you get one sweep through the frequency range. And this is going to take a while. It's going to take 146 seconds. And again, this may seem a little tedious, but this is part of the presentation to really drive home the difference in the methodologies and the superior capability of time domain scan with respect to capturing intermittent signals. Going to slowly go through. And again, another thing to point out is that we do have pixelization going here. So you have a wide span, and if you don't have 970 megahertz, if you have 801 points, each pixel is going to represent more than a megahertz. Each measurement point, that is. And there it is. So we found our signal at 700 megahertz, but we still have not swept through the entire spectrum. And we can just end it a little early here, but we get the point that to sweep per the standard, 146 seconds in a frequency swept mode. Okay, so now let's go to time domain. So again, we're going to set the dwell time to 15 milliseconds, which is the standard. And what you're going to see is the event is detected very quickly. Okay, so what you saw is that it's still spending 15 milliseconds at each group of frequencies. It can just chunk through the spectrum so fast, and because it's measuring all these frequencies in parallel, you're not going to miss anything. So that shows the superior speed of time domain scan. Okay, so now let's zoom in. So before we were wide, we had this pixelization issue. Now it's the exact same input signal, and we're going to zoom in between 650 and 750 megahertz. Per the mill standard, sweep time is 15 seconds. So what we're going to see is many sweeps are required to properly capture the signal. It's going to take nearly 3 minutes despite the 15-second sweep time. In addition, the user must be aware of time aliasing that I'll talk through the video while we're waiting to correctly capture it. Okay, so we have manually set the sweep time per mill standard 461 to 15 seconds. We are sweeping from 650 to 750 megahertz with a pulse period of 10 milliseconds and a pulse duration, again, of 10 microseconds. So now what you see is a bunch of spikes. You can detect that there's something there, but you really don't know what it is, and for sure you don't know the exact peak of the signal because you don't know that you've captured all the signal. Is it a continuous spectrum, or are there really these lines that you see? This is going to be one of the longest videos. So again, what I mentioned before was aliasing. So right now the sweep time per the standard is set to 15 seconds. So what happens is if the pulse repetition rate is a sub-integer of the sweep time, then that pulse is going to show up at certain parts of the spectrum, or certain parts, or the capture point is going to be at certain parts in the spectrum, and it's going to be in the same place. So you're going to see these frequency components come in the same areas of the spectrum. And just to make that a little bit more clear while we're waiting for this to properly capture the max amplitude is, say that the pulse repetition period was 5 seconds. So every 5 seconds that pulse is going to come up. Well, if you're sweeping here 15 seconds and it comes up every 5 seconds, then only 3 times during the sweep is it going to be active. Say here, here, and here. So what that means is that in a swept mode, you're only going to capture the pulse in this, you're only going to be measuring the same 3 frequencies when that pulse appears. So you have to make sure that there's no integer multiple of sweep time to the actual pulse duration. I should say pulse period. So now we're starting to get a more clear picture that there's definitely something there. It's not a continuous spectrum, even though the actual spectrum is continuous when that pulse appears. But we still don't have a good feel for what the maximum frequency amplitude is. And there you go. And we are 3 minutes in. So 3 minutes in, I know ahead of time that this is an accurate maximum. We still don't have a set of data that yields a continuous spectrum. And this is long and tedious. So we'll skip the rest of the video, and now we'll go into time domain scan. So now again, the same parameters, same input parameters, same frequency range to sweep, same resolution bandwidth, and the dwell time is set to 15 milliseconds per the standard. So it's the same adherence to the standard. And what you're going to see is a peak is found very quickly. And there you go. In a matter of seconds, you have a closed frequency trace, a closed.
I'm sorry, it looks like we're having technical difficulties. If you could just give us a minute, we'll try to figure out what's going on. Hi again, I'm sorry, we're still trying to figure this out. I'm not sure, Bill, if you can hear me, but we sent you a message through the chat.
Okay. Can you hear me now?
Yes, we can hear you, Bill.
Okay, am I back?
Like you're back. Thank you.
All right, I have no idea what happened. Okay, I don't know if I stopped talking during the last video, or did anybody hear the explanation of this next video?
It was about halfway through the last one,
Ah, okay.
the video.
All right. I can go back. Now my USB is I think I've got a USB problem. There we go. Okay. Okay. So what I was saying here is this was the time domain. Could you hear me during the time domain? I'll just do it in case. All right, so here is the picture of the video of the time domain, and the emphasis was that you sweep through very, very quickly and you capture everything right away because you are measuring all the frequencies in parallel at the same time. Now we'll move to the final video, and what this is it's the same pulse duration as the prior video set, but now we've increased the pulse repetition interval to 1 second per the new signal in the MIL Standard 461G released for industry review. Same resolution bandwidth as before. It's one video that will take you through swept, stepped, and time domain. What we'll see is swept takes a long time. The aliasing is prevalent, like I mentioned in the last one. In the video step, the video shows just long enough to show how long it's going to take for a 1 second pulse repetition interval. And then time domain is going to find this in just a couple seconds. Okay, so here we are. Again, we have the knowledge that the pulse repetition duration is, or method, or period is 1 second. So we're going to set the sweep time to 1 second. We're going to gradually increase the sweep time. And like I said, if the pulse period is a subinteger of the sweep time, then the analyzer is going to always be measuring in the same frequency spectrum when that pulse comes up. So you're only going to be able to see it in certain parts of the spectrum. It's an aliasing of the sweep. We're going to increase to 2 seconds. Again, you can detect that there's something there, but you really don't know what it is. Now we're moving up to 5 seconds. Now we're moving up to 10 seconds. So what this means is that that pulse period is every 1 second it's going to come up. And if you're sweeping at 10 seconds, then it's only going to come up in the same section of the spectrum that it's measuring. So you're never going to measure in between because, again, of that aliasing. You can see from the spectrum that there's something there, but you really don't have a good feel for what it is. Now 20 seconds. So what you're going to see is that when you do detect something, they're always going to be in the similar frequency. So right there, there's 2 measurements. So now when it sweeps through again, that pulse is going to occur in the same part of the spectrum as before because of this aliasing. Right there again, right there again, again, and there again. So even though there's a continuous spectrum every time that pulse occurs, you're not capturing it. And this is why in this particular signal, again, you're seeing that that pulse comes up at the same time. That's why this methodology for this type of input signal is not a good choice. And pretty soon here we will move to a frequency stepped methodology. And here we go. So frequency stepped, EMI receiver, time domain off. We're doing this with the knowledge that it's going to be 1 second. So the measurement time is set to 1 second. Therefore, the measurement or dwell time in a frequency stepped, you will properly capture that signal. However, because you're dwelling for 1 second at every single frequency that you're measuring, you can see it start to fill in here, but it's going to take a very, very long time. So in this methodology, you will capture it if you have the right measurement time, but it's going to take forever. Now what we're going to do is go to time domain in the exact same measurement time, but rather than doing one frequency at a time, you're measuring that entire FFT bandwidth at one time. So again, measurement second, one time. Now you scan through the spectrum in just a few of the FFT bandwidths. So let me go back to here. And that really shows the longer the pulse repetition period, the more superior time domain scan is. And I'm running short on time because of the problem here. All right, so in summary, so pulsed and intermittent signals are prevalent throughout the industry, and they must be properly detected and characterized. Advances in DSP technology enable new methodologies of time domain scan. Also, what this does is enables a more EMI diagnostic capability, and I'll be speaking that tomorrow. Traditional spectrum analyzer frequency swept methodology has limitations that must be understood to yield the proper results. You have the sweep time, you have to back calculate the number of points and the frequency resolution, make sure there's no aliasing, be cognizant of what the pulse repetition rate is, and then finally time domain scan is a very powerful methodology for detecting and characterizing pulsed and intermittent signals, and up until now it's really been marketed as a time savings, which is true, particularly in the conducted range when the conducted range is in the entire real-time bandwidth of the analyzer. So you can do up to 30 megahertz in real time simultaneously. But in addition to that, it's the ability to capture these intermittent signals because you are measuring all these frequencies simultaneously about a certain range. And with that, I am over with time, so we can go to questions.
Thank you so much, Bill. We did receive a number of questions. I would like to shout out for a few more if you have them. Right now I'm going to turn it over to Scott Nemec, Application Engineer at Rohde & Schwartz, who will address the questions.
Hi, this is Scott Nemec. The first question we have is talking about the examples here are talking about periodic signals, but what would the EMI effects be if it wasn't guaranteed to be a periodic signal? What kind of measurement and sweep is done in this case? Bill, would you like to address a non-periodic signal, or do you want to restrict this to this is...
No, that's a very fair, good question, and for the sake of these videos, there's no way to do it with just a single shot signal, which is why we had to go to a periodic standpoint. But if you're capturing something that isn't periodic, the best you can do is make sure that your measurement time is long enough to capture anything that is there. And yes, this was done from a periodic standpoint, but the point is that you just have to go with what you've got have the best that you can do with that maximizes your chance or your probability at capturing that signal. So if it's not periodic, then how long do you wait? That's part of the guessing game, or not guessing, but that's part of what an EMC engineer has to do is wrestle with the confidence that you're going to capture something by setting this dwell time long enough versus the speed of having it the dwell time shorter and being able to scan through faster. So it's really a trade-off in comfort in maximizing or increasing that dwell time that's going to give you a subjective level of comfort that you have captured what is there.
Thank you for the answer. The second question that we have is there a real difference when using EMI filters with a 6 dB roll-off versus the 3 dB roll-off of a spectrum analyzer filter?
Sure, absolutely. I think that gets a little bit more deeper into the architecture and setting the frequency steps, which I didn't cover. Because you have a 6 dB bandwidth, that roll-off is going to be closer, so you need to have a little bit finer frequency resolution. But most of that is called out in the standards, be it CISPR or MIL standard. So in actuality, that's another benefit of time domain scans. So typically the frequency step in a frequency stepped measurement is about every third of the resolution bandwidth. And that ratio sets the picket fence effect, which is the ratio of the frequency step to the pass band of the filter. However, in time domain, because of the FFT, and what I didn't cover is that the FFT, it does a factor of 2 to get that lower number of computations. Because the FFT is a number of 2, instead of every third frequency step of the resolution bandwidth, it's every fourth. So you really have a finer frequency resolution in time domain. And so that's, again, going from a 3 dB to a 6 dB bandwidth, you need finer frequency steps. That's actually another advantage for time domain.
Thank you. The third question that we have refers to the standard. Is time domain scanning allowed per CISPR 25 for preview and final measurement?
I don't know the individual CISPR, so it's going to depend on which of those standards reference CISPR 16-1-1. And in CISPR 16-1-1, it does call for specifically allow FFT scanning. And Scott, maybe you know that better than I do. I don't know if you're familiar with that particular CISPR standard.
I'm not aware of it calling out CISPR 16, which version of it calls out. It does reference 16. But I'm not familiar with which version, so
okay.
We cannot answer that directly today.
Yeah, so what we'd have to do is go back and look at CISPR 1625 and see which version of CISPR 16-1-1 it references.
Okay. Thank you for answering that. Question 4, they ask, do you know the sampling frequency used in these demos? The sampling rate of the digital ADC of the device.
No, I don't. Scott, maybe you do with the architecture side, but I would point out that it's probably not important in the standpoint that the decimation in the time domain, and when you calculate in the frequency domain, is going to be a function of the particular IF bandwidth used. And the important thing is that the piece of equipment is going to use whatever sampling rate is necessary for the bandwidth that it's measuring. So I don't know the particular sample rate, but via decimation, the effective sample rate is always going to be changing depending on the bandwidth that's set.
Thank you so much, gentlemen, for a great presentation. We're going to have to wrap it up, unfortunately. If we did not address any questions, or if you have any more questions that we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website. We will also send a link to all participants shortly. Please join us for EMC Live 2016, which will take place in April of 2016. Thank you, everyone who attended.